So in Chapter 9, we are going to switch and look at some paired data sets. That just means instead of looking at only one piece of information, we'll be looking at two pieces of information where one corresponds to the other. So just to give you an example of what a data set might look like that when it's paired data, let's say we take a sample of 30 people and we record the height for each one of those 30 people. All right, that's a single variable. All right, that's a regular data set, the type of data set that we've looked at all throughout this course. But let's say instead of just looking at the height for those 30 people, we decide we're going to look at their height and also their weight. So that means for each individual person, we have a pair of data values where X is their height and Y is their weight. And when we write our values paired like this format should look familiar to you. This is just like an ordered pair, which you see in algebra. We can plot points based on the paired data, and we can use that to look for a linear relationship or a linear pattern that occurs when we plot those points. So in 9.1, we're going to be looking for a linear correlation, and that's just another word for a linear relationship between the two values X and Y. All right, for whatever data set we have, but for example, is there a linear relationship between a person's height and a person's weight? So we're going to start by talking about what we would look for in the graph, right, or the scatter plot, because we're just going to be plotting points here. And again, it's going to be about looking for a linear pattern or a linear relationship. I'm going to give you an example or three examples here. Let's say that we take a paired data set, we take our points X and Y, we plot those points. And when I say plot those points, I mean just like what you do in algebra, right? Each one of these would have an X value and a Y value. Now, if we plot our points and we see that for the most part, they are following along a line with a positive slope, then this would tell me that this data has some positive linear correlation. Now again, we're not looking for perfection. They're not going to fall in an exact straight line. We're just looking to see that the points follow a linear pattern, at least kind of stay pretty close to that line. And as you know, we can talk about lines with positive slope. We can also talk about lines with negative slope. So another example of a linear relationship would be a scatter plot that looks like this. Right? So in this case, I see that my points are, for the most part, staying pretty close to a line, but this line has negative slope. So this would tell me that my data has some negative linear correlation. Now, if neither one of these things occur, so if my points are in some other type of shape, or if my points just seem like they're random, regardless, if I cannot find a linear pattern, like what I'm looking at here, then I would say this data, doesn't mean it has no relationship at all, I would just state it has no linear correlation, because the points are not following a linear function. Right, now we're going to look at some graphs in just a minute, but I also want to go ahead and introduce you to the second way that we're going to look for linear correlation, and that is with an actual numerical value, so a number, right, something a little bit more concrete. So once we look at our scatter plot, we're going to get an idea if we have some possible correlation. But then what we're going to do is we're going to calculate a number. It's called the linear correlation coefficient. And what this number will do is reinforce what I'm seeing in my scatter plot. Now, I've given you the formula here for the correlation coefficient R. You can see it's a pretty lengthy formula. So we're going to go to technology for calculating that value. But we want to make sure that we can interpret when we get the value of R. So when you calculate the correlation coefficient, the first thing to note is that it will always stay between -1 and +1. And those endpoints are really what you're looking for. So any correlation coefficient that's close to 1, that's telling you have positive linear correlation. And the closer to 1, the better. The closer to 1, the stronger that relationship. If you calculate your correlation coefficient and it's close to -1, that's going to be that negative linear trend, that negative slope. And if your correlation coefficient is closer to 0, then that's telling you there is no linear relationship between the two. Okay, so let's go ahead and look at some actual data values and see how we would analyze to determine if there is a linear relationship. So you'll notice in the example that I've pulled here, we have paired data. So for each of 12 students, we're looking at the number of hours spent online, that's our X value, and then the corresponding test score is our Y value. Okay, so again, each one of these can be looked at as an ordered pair with an X and a Y value. Now, I'm asked to first display the data in a scatter plot. Now again, that just means I want to plot each one of these as an ordered pair, all right, like 096, 185, and so on. To make sure that I get an accurate graph, though, I'm going to go ahead and put this data in StatCrunch, and I'm going to pull the scatter plot from here just to make sure that I get the most accurate representation. So the easiest way to get to your scatter plot here is going to be to go to your Stat menu, come down to where it says Regression. We'll talk about what that term means in a little bit. And then all we're looking at right now is a simple linear regression. Okay, so I'm going to click here on Simple Linear. Now, there's a lot of different things you can put in this box right here, but all you have to do is specify your X and your Y. All right, what are your X's, what are your Y's? So I'm going to do that here. I'm not going to mess with anything else on this page, and I'm going to hit Compute. All right, now, what you see on the first page of the output is the numerical analysis. To get to the graph, you need to click on that arrow at the top to move to the second page. First page is numerical analysis, second page is the graph. And what we're seeing here is a plot with each ordered pair X, Y, and it also shows me the line of best fit, all right, the line that follows the points as closely as possible. All right, so this is what you're seeing right here. I went ahead and pulled that scatter plot so that we could see exactly what was happening. Now you can see right off the bat that the line of best fit here definitely has negative slope. And it looks to me like the points are staying pretty close to that line. We have a couple, that might be a little more questionable. So we'll look at the correlation coefficient as well. But just based on what I'm seeing in the scatter plot, it does look to me like there's some negative linear correlation. Now again, sometimes the graph can be a little bit subjective. And so that's why, so this is part A, that's why in part B, we're going to take our numerical analysis a little bit further, and we're going to calculate the correlation coefficient. So now what I'm going to do is I'm going to look at the numerical part of the regression. This was the first page. And again, there's a lot of information that's given here, but what we're looking for right now is this value right here, the correlation coefficient. And typically we write these to 3 decimal places. So I'm going to report that correlation coefficient at negative 0.831. All right, now we'll pull some of these other values a little bit later, but right now, that's all we need to look at. So I've looked at my graph, my scatter plot. I have looked at the correlation coefficient, and now what I want to do is talk about any possible linear correlation. All right, so I'm going to come over here and kind of interpret my results based on the scatter plot. Right? It did look like there was a line that they were following pretty closely with negative slope. Based on the correlation coefficient, that value of R This is a value that is pretty close to -1, right? Negative 0.8 is pretty close to -1. So based on those two things together, I would conclude that this data set has some negative linear correlation. Okay, so this is what you're going to be doing in section 9.1. Everything's going to come from running a linear regression. You're going to look at the graph, you're going to look at the correlation coefficient, and pull that together to determine if you have any possible linear correlation. Now, one last thing to note, when you look at the correlation coefficient, that value of R, so I'm going to come over here to the side, sometimes you'll be asked to compare that to a critical value. So if you're wondering, how do I know if it's close enough to 1 or -1? One thing you can do to keep it from being so subjective is you can pull a critical value from a correlation table. All right, now I'm going to go pull that correlation table so that you'll know what it looks like. All right, there are actually two tables on the same page here where I posted this for you. I think I just pulled the one table for you guys. But either way, you're looking at table 11, and it states its critical values for the Pearson correlation coefficient. Now, it's very easy to read. All you have to do is look up N, which is your number of pairs of data values, and then a level of significance. So let's just say, for example, we wanted to pull a critical value for a 5% level of significance for this particular data set. All right, now I'm going to go back and pull the information that I need. So I have 12 pairs of data values. And like I said, I'm going to use a level of significance at 0.05. So I could come over here to my correlation table. All right, I could look right down here at 12. And at a level of significance 5%, I would have a critical value at 0.576. Okay, so if I were asked for a critical value here, I would report that critical value at 0.576. And what I can do with that is I can see if the absolute value of my correlation coefficient is greater than the critical value. Now we do absolute value because we're looking at -1 or +1. But if that happens, then I can conclude there is significant linear correlation. And you can see that would happen here, right? The absolute value of our correlation coefficient would be positive 0.831. That is definitely greater than 0.576. And so that does tell me that this data set has some negative linear correlation. And just so you know, it would work the same way for positive linear correlation. You would compare to the same set of critical values from that table. So this is what you can do anytime you're not sure if you are close enough to -1 or +1. You can go pull that critical value, do a direct comparison, and if you're greater than that critical value, you know that there is significant linear correlation. Okay, so again, 9.1 is going to be all about, is there a linear relationship? In 9.2, what you're going to do is say, okay, if there is a linear relationship, then let's write the line that best fits that data. Let's write the equation of the line that best fits that data. And we're going to do this just using a basic slope-intercept form, right? Y equals mx plus b. Again, this should be familiar to you. M would be the slope of the line, and b, the y-intercept. If we can find the slope and the y-intercept, we can write the equation of that line. Now again, I want to show you that there are formulas. This is just calculated from the values of x and y. But these values are also reported when we run our linear regression. Okay, so if I stick to the same data set, because we've already determined there is negative linear correlation, we've already looked at the scatter plot and the correlation coefficient. All right, then what I can do is I can use this linear regression to write the equation of the regression line. Now, I just showed you the basic format, y equals mx plus b. The main thing that you have to remember, again, is that m is your slope and b is your y-intercept. So if you look right down here, it says parameter estimates. You are given the slope for that line of best fit as well as the intercept for that line of best fit. So if I want to write the regression equation, I'm going to write it in terms of y hat. We just use y hat because it's an estimate, not the actual value of y. But all I'm going to do is plug in the slope, negative 4.067. Slope is always the coefficient of x. And then I'm going to plug in that y-intercept at 93.970. So this right here is what we call the regression equation. But all that represents is this line, this red line that we're seeing, which follows the points as closely as possible. And you should be able to see, you know, if you look for the y-intercept, it crosses the y-axis a little above 90, 93.970. It does have a negative slope, a negative rate of change right around -4. So it's writing the equation of the line that we just said our points were following. Now, the reason this is useful for us is because we can use the regression equation to make predictions for other values of x. Okay, so for example, in part A here, I want to look at what should happen for a student who spends 4 hours online. All right, I want to use this to estimate the test score. So I'm just going to go to my regression equation. It says y hat is negative 4.067 times x. So I'm going to plug in the 4 hours plus 93.970. And if I evaluate this regression equation, it's going to give me an estimate, that's why we call it y hat, for the corresponding test score. All right, exact value I get is 77.702. But what I'm looking at there is for a person who spends 4 hours online, I would expect a test score somewhere around 78 based on the linear relationship that we saw when we constructed our graph and we looked at the correlation coefficient. And I can do this for any values of x as long as I don't go outside the range of my data. Right? So if I want to look at 8 hours spent online, the regression equation does not change. All I'm doing is evaluating for different possible values of x. And if I look at the change in my test score, for 8 hours spent online, I would expect a test score right around 61. And notice, you know, we're doing this for values of x that were not in the original data. Like we had 3s and 5s, we didn't have any 4s. We had 7s and 10s, we didn't have any 8s. So we're now using this to predict for those values. So another one that we don't have in our table here is a person who spends 9 hours. So if I want to make that prediction, like I said, the regression equation does not change once you find it, but you can plug in different values of x. You can evaluate that regression equation. And for a person who spends 9 hours online, we would expect the test score to be somewhere around a 57. Notice these are going down because the line has negative slope. So the more hours spent online, the lower that test score is going to get. Now, I made a statement just a minute ago. I said you can plug in any values of x as long as they stay within the range of your data. So notice our x values in the data set range from 0 to 10. So I'm good to plug in any values between 0 and 10 because I know the linear relationship is present. But if I try to jump outside that range of x values, I don't know if the linear relationship still holds true. So for anything that tries to kind of jump away from the data, even though I could plug 15 into my equation, it's just a number, I can plug in anything I want to. For a case like this, I'm not going to do that. I'm just going to state this would not be a meaningful prediction. And again, the reason is because it's outside the range of data that was used to write this linear equation, so we just don't know if the linear equation would still work for those values. So that's just something to kind of be cautious about. You can plug in any values of x within the range of data that you use to write your equation, but if you try to jump outside of that, then what you're going to be looking at there is not a meaningful prediction.